hazard rate distribution, and they also are in literature. However, this power hazard rate distribution, unlike the other ones that have been studied and is in existence in literature, uh, it has been shown that the upside down bathtub shape hazard rates has not been discussed. And the actual distribution that always shows this upside down bathtub shape hazard rate distribution is the inverse of every distribution. And we could also see that one of the advantages that makes clear distinction of inverse distribution is that it is not parsimonious. It uses the number of parameters it uses is the same as the number of parameters as the parent distribution or the baseline distribution. And that is the reason why we decided to look at this particular distribution. So as we went ahead, we continued, we looked at deriving the PDF, CDF, SF, which is the survival function, the hazard rate function, and also the quantile function of the inverse power hazard rate distribution. And it is shown in the slide in equation 5, 6, 7, 8, and 9. And we went further to look at the curve which displays the PDF and the H, that's the hazard rate function of the inverse power hazard rate distribution for different values of the parameters A and B. From the curve, we could see that's the PDF curve. We could see that it shows a modal. It shows a unimodal shape or like, and that it can also track an asymmetric data. Then for the hazard rate function, we could see the upside down top shape, which shows that the this particular distribution can be effective for increased failure rate systems. Other statistical properties we also looked at them. One is the random number generator, which we were able to develop from the quantile function. Then we looked at the raw moments, and from the raw moment we made a remark that the raw moment of the inverse power hazard rate distribution can only exist if the R, which is the the power of the X when we want to generate the raw moment, if it is greater than the what was it called, the shape parameter plus 1, and then the mean and the variance can also exist if the shape parameter is lies between, there's something omitting there, I omitted there, lies between -1 and 0, and then the shape parameter, if it is greater than 1, that means the variance can also exist. Then the median, the mode was also obtained. The other statistics, the PDF and the CDF, were also obtained. We also looked at the Rennie's entropy, which is usually used to measure the uncertainty for every random variable that follows a particular distribution. That we were able to get in equation 16. We looked at strength reliability, strength reliability, which when two random variables that follows this inverse distribution that are independent, when they are compared and they are not compared, sorry, when their strength and stress are looked upon, and the shape parameter is equal, the stress strength reliability gave us what we have in equation 17. Then after looking at the properties, we went ahead to look at the estimation of the parameters of the power hazard rate distribution. Looking at the estimation, we were able to look at uh, estimators that can give us the estimates of these parameters. And from what we have here, the first parameter, which is the the parameter, the shape parameter, no, the rate parameter can easily be derived, but the no, the rate parameter can easily be derived. That's about equation 20 there, but the shape parameter, which is equation 21, can only be solved analytically, which we did that using numerical approach. Then from there, we looked at the consistency of the estimators by simulating the data. And from what we did, we set some values for A and B, and then varied N as it increased. And from what we saw, from the table, we saw that the average estimate, which is AE, when the sample size increased, was able to converge to the values of the true parameters. And looking at the AAB, which is the absolute average bias, and the ROSME, root mean square error, we saw that their values decreased as the sample size increased. And from that, we said or concluded that the estimators provided by the MLE is consistent to produce a good estimate for the inverse power hazard rate distribution. Then after that, we applied it using real data sets. And that real data set was the airborne communication transceiver data as reported in Harvard 1964 and May 2018. We used the goodness of fit measures, the Kolmogorov-Smirnov test, and also the AIC and BIC to ensure that we selected a model that best fits the data. And what we now did was to compare the proposed distribution with a set of other distribution existing in literature. And from what we obtained, we presented it on table 2 as that there in the slide. From there, we consider the negative log likelihood, which we represented with L, and then the AIC and BIC. And what we saw there, we saw that, okay, the PHR is the power hazard rate distribution, which is the parent distribution of the inverse power hazard rate distribution. The other one is the inverse exponential distribution. The other one is the inverse relay distribution, and the other one is the inverse one parameter Weibull distribution. From what we saw there, we saw that the inverse power hazard rate distribution have a lower matrix of comparison. And the KS, which is the Kolmogorov-Smirnov test value, supposed to be minimum compared to other, say, or compared distribution. From there, we concluded, okay, from there, after that, we had to get the fitted PDF, CDF, and QQ plot and PP plot for the inverse power hazard rate distribution. And at the end, we concluded from what we have done that the inverse power hazard rate distribution as proposed by us performs flexibly well compared to other distribution that we compared to other distribution used in the study based on the data. And that is where we concluded our study. Thank you very much.
Let's clap for him. Mr. Lemche, thank you for the
Dr. Lemuche, sir.
okay, Lemche, for the wonderful presentation.
Thank you, sir.
So, my beloved audience, this is the time for us to ask him. We are free to ask questions, observations, comments. Anyone here? Comments, observations, questions? I guess we listened attentively to him. So anybody here? Okay, one. Okay, yeah, please we give it to our two. Very good.
Good afternoon, everyone. I don't know if I missed it, but I didn't see your aim and objective of this study.
Okay.
I don't know if I missed it. I don't know.
Okay. Okay. We shall that one.
The presenter, sir.
Yeah.
I have questions here. One is, he said that the studied distribution has equal number of parameters with the parent distribution, and that is why it is studied.
No.
That's what you said. Yeah,
Okay.
that's what I'm saying
Okay.
it. If that is why, you
I
can
say
let
one
us
is
know.
one of the advantages.
You-
One of the advantage.
Okay.
Yes.
That was at the time of conclusion. Then you also said that in the graphs you showed there, that it has
A unimodal.
upside, not unimodal.
Okay. The H.
Yes, you
Yes.
said that
Okay.
there's an upside down failure rate, failure rate.
No, bat top, upside down bat top, which
Okay.
indicates increasing failure rates
Okay,
of a system.
understand it from your
Okay.
graph. That's what
Okay.
I'm asking.
Why the other? Please, you just respond to
Okay.
my sister's
Anyway, it's theory. It's theory, theoretical work. And for wanting of a what's it called? Wanting of a space for the slide. You know, I know the last season we are told to make 15 slides. So maybe in the paper, you understand, the full paper is there. She asked, why is there no aim and objectives? Eh, yeah. Okay. Hmm. Okay. Tell us the aim. Okay. Okay. The aim is to propose a new distribution called the inverse power hazard rate distribution. We have set of objectives. The objectives is to look at the properties of the proposed distribution. The second one is to get to estimate the parameters of that distribution. Then the third one is to apply it, the applicability in a real life data. So that is what we did. And then, okay, yes, to compare in existing year. Okay.
Okay, thank you very much, presenter. We appreciate that wonderful effort and the presentation. Um, just I don't know, maybe it is in your full paper, but this theory you have presented is wonderful. It's fine. But the assumptions underlying what you have developed is not too clear to me.
Okay.
Now, when can this what's the name of this model you distribute?
Yes.
Sorry, the
Distribution.
inverse power hazard distribution.
Inverse power hazard
When
distribution.
can this be used? It's not stated when you were making your presentation. So I think it will be fine if we can do that. And then the other thing is that you have said it performs well compared to other distributions you considered in your study.
So for the same data.
For the same data.
For this data.
Okay, the same data.
No, for this data it performs
Okay, for this particular
because
data.
another data can come, it will
Okay,
not perform
okay.
well.
So that is the area I was going to.
Yeah.
You have used this only on one data type.
Mm.
For you to be able to make oh, oh, okay. Okay, maybe I missed those conditions. Is okay. I think I will rest the question. Thank you.
No, that one is for that statistical property, but for the distribution itself, there is a ban of its existence. Uh,
The other question for the other yeah, I was going to is, the issue of consistency.
okay.
You have given conditions. You have given conditions, and you tried this thing on a particular data.
Mm.
For you to be able to make generalization, or for you to convincingly
Mm.
conclude it performs better, you have to try it on different data
Yes.
sets, and
At least two.
and and,
At least
and then
two.
come with your
Mm,
conclusion.
yeah.
I don't know if that is done in this paper. If it is not done, I think it will be fine. You add something in that direction.
It's okay, sir.
Thank you.
I guess any other comments or question, observation? If there are no, we need to move forward. Thank you very much for your wonderful question. Really
Thank you.
appreciate. Can we give a hand of applause?
Thank you.
So we'll quickly move to our second speaker for today.
You don't see our inverse power
Chinelo.
hazard distribution.
Okay. Please let's project Chinelo's paper.
That girl always did their talk story. The other boy will concentrate more than this girl. Mm. To find out from these people this time what actually they want, what actually will they give us? Will they give us certificate of presentation?
It's okay. We have the second presentation before us now. Chinelo Chukwelu. She will be talking to us on optimal control of an infectious disease using probability what distribution. Like we said, you have 15 minutes to speak to us. You can go ahead.
Think tomorrow that opening ceremony get when Cody they come. All these two more. Hey, sorry.
Standing on the existing protocol, I'm here to present my work on optimal control of an infectious disease using probability distribution. When we talk about optimal control, how to control disease, that's what we are talking about in this optimal control. Then infectious disease is one of the leading cause of death globally. So how to control all these infectious disease, that's what we want to show. Then we developed a distribution called the type 1 heavy tail top loan distribution, using that of the type 1 heavy tail and then the top loan distribution to develop it. And then we derived the statistical properties. From there, we now developed an optimal control model. Then in the statement of the problem, we stated that because the widely used one is the deterministic optimal control, but here we are going to develop the one that incorporates this stochastic approach. According to Russell and Conniff 2025, the deterministic approach cannot be used because in a real life situation, modeling disease is not deterministic because it is stochastic in nature, so it can incorporate all this randomness in it. So we now developed the optimal control using this probability distribution. Next, just next. Okay, this is our methodology. We developed equation 1 is the type 1 heavy tail distribution, is the CDF. Then equation 2 is the PDF. We now have the one developed, that is top Leon G family by Ashmani et al. 2016. The CDF is equation 3 and the PDF is equation 4. Then replacing that baseline CDF in equation 1 with that of the top Leon G family in equation 3, we now have the CDF of the type 1 heavy tail top Leon G family. Also, substituting equation 3 and 4 into equation 2, we have the PDF of the top Leon of the type 1 heavy tail top Leon distribution. We now use relay as the submodel. The PDF is given in equation 7 and the CDF in equation 8. Substituting that equation 8 into equation 5 gives us the CDF of the type 1 heavy tail top Leon G family. And this is the plot of the PDF of the type 1 heavy tail top Leon relay distribution. As we can see, it is skewed to the right, showing that it's heavy tailed, that is tilted towards the. Then the equation 11 and equation 12 is the survival function and the hazard function of the type 1 heavy tail top Leon relay. We now have equation 14 as the Renyi entropy, which is the measure of randomness or uncertainty. Figure 2 is the hazard function plot of the type 1 heavy tail top Leon distribution. The first one is a bathtub, the other one is right skewed, the third one is left skewed, the fourth is, then E is the exposed, the I is the infected class, R is the recovered class. We have the recruitment rate, we have the transmission rate as rho, mu is the natural death rate, then phi is the immunity. We have hectare to be rate of transmission into the exposed class, gamma is the recovery rate, then delta is the death due to the infection. Continue. Then equation 22, in this equation 22, we incorporated the control measures. And this control measure, we are using like face mask and treatment for the control measure. Then we now use our hazard rate, because this hazard rate is instantaneous rate of recovery, given that the person has not recovered before. That's why we incorporated the hazard rate, so that we will now see the behavior of this model. Because from deterministic aspects, the rate of recovery in deterministic shows that if this person have the disease, it's the same rate. That is, if I recover today, the same time, that is the time the another person will recover, and at the same time another person. But with this probability, that is the hazard rate, it shows that it's not the same time of recovery. Then we have the objective function given as equation 23. This objective function is like, what are we going to achieve? Here, we now want to minimize the number of infected individuals and also the costs. We have the C1 to be weight associated with the cost of infected individual, C2, weight associated with the cost of prevention control 1, C3, the same weight associated with cost of treatment. Then we have this Hamiltonian function. The Hamiltonian function is the kind of tells us the optimality condition, those conditions that we need to meet before we can now say yes, that this this model is optimal. So the Hamiltonian function comprises the objective function and then the co-state variables. That is the zeta 1 to zeta 4. We have zeta 1 to zeta 4 because we have the susceptible, exposed, infected, and the recovered. The co-state, this is the equation for the co-state. We now differentiate it with respect to each of the state dynamics. We now have the one for equation 25 for that of zeta 1. We have, oops, sorry. Yes, we have the zeta 1 for the first one, that is for the susceptible class. Zeta 2 is for the exposed class. Zeta 3 is for the infected class. And then zeta 4 is for the recovered class. And then our t is equal to 0, 1. That is the final time. Then we have the optimality condition. After differentiating with respect to those control, we now have equation 26 and equation 25. 0 signifies that they don't use the face mask or there is no treatment, while 1 signifies that they use either the face mask and also treatment. Then the result for the type 1 heavy tail top leon distribution, we have our n to be 25 to 200. These are the methods of estimation we used, and it shows that they are decreasing, that is trending towards the original value. Next one. Then we now compared it with different distribution. From the p-value, we can see that our own distribution performs better than other distribution. Also, the AIC and other things. Then for the optimal control, so I've not done the simulation, but I'm anticipating that the incorporation of this hazard-driven recovery into that SEI framework, together with the treatment as an optimal control, will significantly alter the epidemic dynamics to the baseline and also give us a better output. Thank you.
Let's give you our applause. Thank you. Spoken well. It was not such a case just now making advocacy for the same thing. So I think it's paying off already. Questions, observations, questions, please about optimal control. Person one, any other person? Okay, the beginning. Okay, so you have your question.
My interest is on the introductory part of it. Let me see it again. Where you mentioned the deterministic and the
When I
non-deterministic,
okay,
deterministic and the stochastic.
within
In,
this
in the general linear process, we have the deterministic and the non-deterministic. Okay, there's a place you say that the deterministic don't capture well. I wanted to see it again because
statement of truth.
the two aspects of the linear model, general linear model, is very, very important. The only thing is that most often the mathematicians dwell on the deterministic aspect of the model, while the statisticians dwell on the stochastic or probabilistic aspects. Okay, so if you have read through a mathematician's work, you also appreciate what they are doing. Are you getting it? So we too, they also appreciate what we do. That is why in literature you see some uh, authors will say in mathematics they will leave the probabilistic aspect to statisticians, and when we are writing, and statisticians will say we'll leave the deterministic part of the work to mathematicians, which means that if mathematician and the statistician will come together and build the model together, we'll have a better result. Thank you.
Thank you.
Thank you for that comment.
Yes, sir.
Like, African mode open, through like mathematicians, model and see how they fit. Mathematicians with the data, like data driven approach, the one as well. So thank you for the discussion. Any other question? Any other question? Okay. Let me. Yeah.
Okay, thank you very much. Um, in your estimation technique, you made mention of using maximum likelihood estimator. Um, I want to know, is it that whenever you are estimating the hazard function,
Is it?
is it that whenever you are estimating this your optimal control model using probability distribution, you must use maximum likelihood estimator, or that there are other possible estimators that you did not consider?
Okay. To
In
the
essence, what informed the choice of the maximum likelihood estimator?
that I'm using. The okay, you can use least square approach for it. But because now me, I'm using this hazard function to incorporate it. So I need to estimate those parameters. Do you understand? Using the maximum likelihood. Yes, for my own aspect of the work. But you can use other this in least square. Though I didn't try it. Yes, sir.
The question was trying to ask that maybe why the choice of ML. And we know that there are other estimators. Why the choice, or why are you using it here? Okay, you want to help us? Okay, there's a comment. Hold on, let's see. Correct.
Thank you, sir. The issue is that you were mentioning least square method. There are so many methods.
That's
But
what
this
I'm saying,
maximum
correct.
likelihood is the one that considers the probability distribution.
Yes.
So the maximum likelihood just is a better option
Option
in
to
this
those
case
ones.
to the least square method, because least square just dwells on error
And
for
no,
forecasting.
because he was asking for optimal control, like if you are using the deterministic approach alone, you understand? They use
But let me also say, as far as model is concerned, as far as social packet, fast distribution. So the ML is the best.
Yeah.
It's the best, and it's gives you to grow. But there's another one that is white call it like it's optimal when it comes to the aspects. Go and look at it. But we only have that I should say quick one. So go and come out about that one.
yes, sir.
Any other observations? Okay.
Hazard rates curves. Hey, hazard rate
Curve.
curves. Those curves. That's where my yes, the curves.
No, not that one. Not
Continue.
that one.
Uh-huh. Yeah. Just like contribution, okay? Maybe in your work, look at how possible systems that follows this pattern, okay? Because it's not only presenting the curve. You understand? There are some systems that
Follows.
follows this, okay? So you just look at them and track them.
Thank you.
Thank you.
Thank you very much. And I think there are no ways to thank students for courage, because they want to do always and no matter how bad you are, of course, we come to all Fa? Okay. I know. We say, I think this is don't worry, let them project it first. I did want to. My mind is what we need to do that whole conference.
It's not starting in life.
Is there anything you show that I don't have to go for the last time?
Even if she feels smart, she's sweat. I don't think so.
That was for the once you check too much, sometimes you okay. Because I know in Uze Lawrence is going to speak to us on the old Tiesia Kumaraswamy distribution, properties and application. So Uze, you have the floor. Talk to us.
Okay. Thank you very much, Prof. Permit me to stand on the existing protocol. I'm to present this paper on the topic, the Alt-Tezak-Maraswamy distribution, looking at some of the properties as well as the application. Probability distribution has actually been very useful in analyzing real-life data. Lot of probability distribution has been in existence, the classical ones, I mean the ones that have been from the beginning. And as a result of the improvement in the use of distribution, we discover that some real life situations cannot be properly analyzed with those classical distribution. Hence, the improvement on this distribution to a fit, or rather to be able to analyze real life situation. Tezat distribution is a distribution that was first introduced by a French biologist to study the mortality rate in some domestic animals, a result of aging in 1934. After a long gap, Mute in 1977 looked at the properties of this distribution, and in his study he was able to disclose that yes, this distribution has a heavy tail, which makes it a good alternative to some other distribution that are also exhibiting the same feature. Now, the major drawback of this distribution is that it is not able to analyze. In fact, it is majorly right skewed. It is not also able to analyze scenarios that have decreasing hazard rate, better hazard rate, and so many others. So this is its handicap, and so many literature, so many persons have worked on this, trying to improve on this work, as we can see in those literatures. The distribution itself, the PDF and the CDF are given in equation 2 and equation 1 respectively. That is that of Tezat, and the Kumaraswamy distribution introduced by Kumaraswamy in 1980. The CDF and the PDF are given in equation 3 and 4 respectively. So many other work has been done, like we said. So many techniques has been introduced in literature to improve on these classical distributions. One of the commonly used in the recent days is the work of Azetra et al. 2013 that introduced a framework of combining two variables. One is the transform and the other is the transformer, in order to generate a new family of distribution, or rather distributions that will perform better than the baseline distribution. In this our work, our interest is to improve on the Tezat distribution using the odd ratio operator, of the Kumaraswamy, and the Tezat distribution as the generator in the transformer framework. So doing that, we use capital R of t and small r of t to stand for the CDF and the PDF of a random variable t. Then we also define, according to the work of Zatra, that is the framework of Tx, we define a composite function, that is Z is a CDF, which is a composition of any baseline distribution, and which must satisfy the probability conditions you are seeing here. Following these principles, they now define the CDF of the Tx framework as given in equation 5. Like I said earlier, if we take the odd ratio operator of the Tezat distribution and use assume that the t follows a tensor distribution, which is the generator. Y is from the baseline distribution, which we are taking to be the tensor distribution. The odd ratio, use it in that equation 5, we obtain the CDF of our proposed model, which is the odd tensor Kumaraswamy distribution. Don't forget, the aim of this work is to improve on the flexibility of the tensor distribution in handling real life situation. So this is the PDF of our proposed distribution, and the hazard are respectively given in equation 7 and equation 8. We can see the display, the plots of the PDF as it can be decreasing, increasing, symmetric, right skewed, left skewed, as well as what I call mini modal. That is, it can go down and then go up. Permit me to say is irregular shape, of which in real life situation there are data like that. The hazard can now accommodate beyond what the tensor itself can do, can accommodate situation with better as well as increasing hazard rate. We look at some of the properties. In order to derive these properties effectively, we did the series expansion on the PDF of our model. And that is what you are seeing in equation 9. We also derive the quantile function for the purpose of generating data, which is the case in many real life situations, which the quantile function is always defined as the inverse of the CDF. As you can see it there, we are taking Q to be from 0 to 1. So equating that Q, which is the value of the quantile at any point, to the CDF, simplifying, we have equation 11. Trying to make Y sub Q the subject of equation, we observe that this equation in 11 is not linear. So we bring in the concept of lambda W function to break this down as defined on the board. So doing that, we have that expression and have our quantile function as shown in equation 12 with several simplifications. Going further, we also looked at the moment, which is normally the integral within the interval of the random variable of the product of the the random variable raised to the power of k and the PDF. Using the result in the series expansion in the place of the PDF, we obtain that as you are seeing it there. And doing the simplification, we get our moment as shown in equation 11, where A1 of A, B, C, D, H is as defined there in that expression. That expression is arrived at during our series expansion. It follows that the central moment is also defined in equation 14, through which we can obtain our mean, the variance, the skewness, and all that. Okay. We also derive the moment generating function following the basic definition, and we obtain it as shown in equation 15. The distribution of other statistics is also derived in this study as defined in equation 16. Bringing in our PDF and our CDF, we have the expression that we have in equation 17. Using the same series expansion idea we used earlier, we were not able to substitute directly the initial series expansion because in this case there is CDF involved. So we took it gradually and we obtained the result as we can see in equation 18, where A4 is also defined there, which we obtain in that process. Now, our estimation, we consider the maximum likelihood to estimate the unknown parameters. The likelihood function of the PDF is given in equation 19. When we take the log likelihood, we obtain equation 20. To obtain the maximum likelihood of these parameters, we now have to differentiate that equation 20 with respect to the parameters, as we can see in equation 21, 22, and 23. Obviously, these three equations are nonlinear, and we cannot just solve it directly. And so we employ a Newton-Raphson iterative method to explore this estimation using this R software. So examine the performance of this the estimates, the maximum likelihood estimate of this parameter. We conducted a Monte Carlo simulation study considering the sample sizes 25, 50, 100 to 500. This is simulated 10,000 times. We pick the values of the parameters in two cases, as we can see displayed on the board. The measures of the performance here majorly is based on the bias and the root mean square error. As we can see on this table, as the sample size for each of these parameters increases, particularly you see that the root mean square error decreases, it reduces and tends to 0. So for all, both for case 1 and case 2, and for all the parameter alpha, beta, and lambda. So with that, we are able to say that yes, maximum likelihood estimation for this model is an efficient one. That is what I've just said, the summary of the result from that table. We now look at real-life application of this data set. The first consists of data from a petroleum sample. The second, as secondary data, it has been considered by Cordero and Brito before. So we looked at it to apply our model in comparison to some existing model. Don't forget, these are model handles random variable or rather data set on a unit interval between 0 and 1. So we compare them with that same data set and models that are also on a unit interval. As we can see displayed on this table, from the summary statistics, we can see from the KS particularly, others are also there. It follows from the KS and the p-value that our model, the proposed model, is performing better than this existing, the Odd-Lomas Toplion, the Weibull Toplion, the Marshall-Okin exponentiated Kumaraswamy, the exponentiated Toplion, and unit chasers. It performed better than all of these. Continue. This displays the fits of that model, and we are also seeing that yes, our model performs better. The second data also is on a unit interval. We also applied it to the same model that we are comparing with, and from the table there, you can see that our model have the lowest PS value and the highest P value, which shows that it performs better. In the same way, you see the plot, both the plot of the fitted PDF and so in conclusion, we proposed a model in this study to improve the flexibility of the Taser's distribution using the odd ratio operator on the Kumaraswamy distribution and the Taser's distribution as the generator on the TX framework. And we call this the odd Taser Kumaraswamy distribution. We studied some of the properties, we applied it to data set, and we can see from all these that our proposed model performs better than the model we compared with. In conclusion, we have been able to introduce and propose a new model that is more flexible, very flexible to handle a lot of data in real life situations than the existing ones, particularly from this TESA's distribution. We also applied it to data and show that yes, it's not just flexible, but it also handles real life data better than some existing models in this um, in handling data on a unit interval. Thank you.
Let's clap for Mr. Nze. Thank you again for one of. I think you will agree with me that Nze is not just or he has not just presented well, but he's a teacher because it's audible, the way it speaks, and we all, I believe everybody heard him very well. So thank you again for that
Thank you, sir.
wonderful performance. Please, time for questions, comments, observation one, any other. Okay, let's start with you. There is okay. There is the small ticket. Have you?
I have two. Okay, one is a question, and then the other one is just observation that need to be. Let me start with the observation. Please go to the table of simulation, the simulation table. The simulation, just pointing down. Yeah. Yeah. And you mentioned bias. Yes, sir. And you are not having a negative value there. If you look at the value of the mean you obtained, they are greater than the parameters. Okay? Yeah. So just observation. Okay. For you to include absolute. Absolute. Yeah. Thank you, sir. Understand?
Thank you. I was to respond to
Then
that. Yes, sir. Thank you.
the other one I want to ask is go to the table of the real life data. Okay. This was one of the questions they asked me when I was presenting my defense. They said you have CVM, AD, and KS. What's the difference between the three? Are they not measuring the same thing? Okay. They are actually. So, that was why when I was doing my own, I had to use one. Okay. You understand? So what I'm trying to say is this. When we get to literature, we see them using the three. Yeah. You understand? Yeah. Possibly there's a reason and purpose why they are using it. Okay. So that anybody that doesn't understand one will use the other one. Okay? So, but the actual sense, we should understand the difference. Okay? It's just, I'm not trying to, but just have it at the back of your mind that it's as if three of them are medicine. Yes. Yes. Okay.
You can also ask yours.
Okay. Hello, Present Asa.
Sir.
I have Dr. Matthew initially, like I presented. So I have two comments and two questions. So the first, let me start with the comments. The first one is this: you're not the first person that did it. This presentation of multiple graphs on multiple plots on one graph, different colors. One would simply expect that they see the one by one, like this color that is green. This is what it represents. This is the distribution, the skewness, before you take the next one. But when you are presenting, you just present all of them as if we already know what they stand for. So that is one. Then the second comment is when you are presenting, as I heard you say datas. So it shouldn't be. It's better
Okay.
for plural, datum for singular statistics.
Okay.
Then my questions. The PDF you are studying, is it a discrete probability distribution or is continuous? Or
It's
is it a
continuous.
hybrid?
It's continuous.
Okay, the use of combinatorics is because there is a function that you need to expand using some functions. I don't.
Sir?
There are some places where I saw you using summation sign and this binomial
Okay.
theorem for
Yes.
expansion.
Yes.
But note it, then you can.
In series expansion, that is where I used it.
That's what I'm asking now. Because when I used something like that when I did the work on generalized moment generating functions. So if there is a function like that you are trying to expand, then we understand maybe Maclaurin's expansion or
Yes,
anything.
yes.
That's
Series
what I try
expansion.
to understand.
That is why.
There is another question. You said you used the Newton-Raphson method, which is an iteration method.
Yes, sir.
We didn't see. Did you display the result here?
Okay, I did not actually. There are a lot of things in this work we did not display because of economy of the slides and order. But in the main work, all those things are there, sir.
Okay, but for the importance of that approximation, one would expect that you present that Newton-Raphson's approximation step by
Okay,
step. Thank you.
subsequently. Thank you, sir.
Thank you, my brother, for that one. That's questions. Okay. You wait. Okay, let me give it to my brother. Yeah, observation. Okay.
Okay, sir.
Please go to the literature. Maybe I'm a literature expert.
The literature review. Go
Uh,
to the beginning. Under introduction. Yeah.
okay.
No. Yeah.
Okay. So the Cison and the other name is can you pronounce it, please? Kumar
Not.
Kumaraswamy.
Yeah.
Kumaraswamy. Just wanted to point out that there are two persons. It's not one person. It's not one person's name.
Okay.
So normally when you have two authors,
Yeah.
you put hyphen.
Okay. Okay. Take it. Okay. Okay. All right. Maraswa.
This one was one that came in class 4 before. Then
The other one did in 1980.
and develop it to what it is
So
today.
Kumaraswamy. Sorry, sir.
Yeah.
I got the point.
Okay.
But Teza did a different work. Has a different distribution.
Because,
Yes. Kumaraswamy did a different work. Had a different distribution. The essence of bringing Kumaraswamy is to bring merging these two using that TX framework to improve the performance of these tasers.
Yes. That's what I'm saying now.
I agree with that iPhone, but the way you were saying it is like I said that Kumaraswamy improved on taser. No, that is the point I'm trying to correct. I agree with you, sir. I perfectly agree with
you. So there's a work differentiated Kumaraswamy. I don't know if you mentioned it. A work that was found before your own.
you. That work. Yes. Yes, exponentiated Kumaraswamy. Yes, I mentioned it in why applying. It's a model on a unit interval. No, it's not in my. It didn't review it.
It was a major work after their work for just.
To say what is trying to say that our literature should be
More robust.
I don't know the adjective to use. Very, very comprehensive. Because normally we have the early work, then the earlier work, and the recent work. So that is the essence of so that you're able to know that you actually have a good understanding of where you are coming from. That is what he has just said. Just give room for our people.
Thank you very much.
Thank you, sir.
It appears I'm talking on every paper. Please forgive me. It is because I want to. It's because I want to learn. It's because I want to learn. Um, a wonderful presentation, and I think I love the theory and everything. But this comment is actually a general comment. What we have as PowerPoint in almost all of the presentations appears to be word point. There appears to be word point. It doesn't look too good. So just PowerPoint is the point you want to discuss on. So you speak to it. Though your presentation was fine, I don't dispute that. But the way the slides are prepared, we have to improve on that. That is by the way. So the other thing I want to learn is about the data set you use. So when you are comparing two things, you must be sure that they are likes you are comparing. So the data set you use it on several other methods, several other is it model, whatever, several other models. So for those models, when they were developed, Was it this the same data set they used? Or the data set they used, does it have the same behavior or properties as this your particular data set? For you to be able to compare what you have done with those other works, my thinking is that you should use the same data set
Go
to
to
be able to
first
compare
data
them.
sets and the table of the
I don't know if
first
my
data
thinking
set
is
and the
correct.
table of the results.
If I'm not correct, I think you will enlighten me. Thank you.
Thank you, sir. Thank you very much, sir.
I hope you understood the question I
Yes.
just asked. So can you respond first?
The first point is taken. Preparing the slides subsequently is taken. Thank you for that observation, sir. Go down, go down, go down. Stop. In these three, the second model, the odd Lomax Toplion distribution, use this data. The third model use this data set. Although the others did not use this data set particularly, but because of time, I did not display the statistics of this data, the descriptive statistics that talks about whether it's right skewed, left skewed, and all that. This is one of the things we first of all examine. What is the flow of this data, behavior of this data? If it is right skewed, we now look for models by its own that have handled right skewed data. That is what we consider in selecting these models.
Okay. Thank you for that wonderful response.
Thank you, sir.
I hear the other question and observations. With the three results. Hear that question. Three different results. From it. Please come and give him my care. We want everybody to benefit whatever you're asking us. So you speak louder a bit. Thank you.
So with these three different results now that you have here, this model that you use,
Yes.
there are three results there, and I'm saying they're having different. They are not the same kind of. So which one now in comparison will you say is best to be used when you want to carry out your needs?
Okay. Thank you, ma'am. I think the first table you are seeing, the table 3, is only showing the estimate of these parameters, maximum likelihood. Now, when we go further, all these things you are seeing, the AIC, BIC, CVM, just like Oga have pointed out, particularly the CVM, ATKS, they are testing the goodness of it. All of them, when in the analysis of data, any model that have the least value of this criterion performs better. The essence of bringing them as many models as possible is just to show that, yes, our proposed model, by our analysis, is performing better than many existing models. I would have just compared with only 2. I can also decide to compare with only 3. But that is the essence of bringing them as many as possible. If you look at all of them, our own is better in all the cases. I don't know if I've answered your question.
Thank you again for that. Wonderful.
Thank you, sir.
Also have a very interesting question. Like I said, in sense of same data or different metrics to compare the same thing, it's just for us to see the consistency so that we'll not begin to say it's by chance that my own is better. So when you have several data sets to compare with and same metrics, you can be able to say, yes, you have validated your model and it's not by chance you are getting those results. I also want to draw our attention in the terms of simulation I've seen here today, for the benefit of everybody here. Some started from sample 25, 50, like 100, 200, 500, and so on. After that someone stopped at 200. See, for standard, we assume 50 to be small, 200 average, 500 or 1,000 large. So I should expect that when you are doing simulation, don't stop at 200. At least if you are even stop, let it be at least 500. So go up to 1,000 so that you're able to see the real nature of your spreadsheet. I think I want to again appreciate everybody here, especially those speakers that have come here today to present their papers. I want to say a big thank you. I also want to appreciate all those that have asked questions. So you are the one that is making the whole thing president and the question. So I want to also encourage further. Let's always work the session because this compared to the applied for it's like a house. This is the foundation. And that shows that these people are more strict than you carry out. Again, I want to thank everybody. The way the copy here today because these are the only speakers who come forth to present their work. I don't know if the other maybe one or two words you want to say. Anybody, maybe you want to make a comment or a general comment? I'll give you the opportunity to do so. Okay, if there are no, I think we have. And I work for remain.
I will claim it here or we go and send to you.
Yeah, you don't know. You take your time and to do it. Yeah, and when you are done, you let me have it too. So you take your time to make the report.
I'm going to use things like this to develop it because we don't have material or we are typing to send to you. And
Let me ask.
they don't have
So normally we are supposed to.
we're supposed to have
Okay, Mario.
okay, your mic.
Okay.
You know, just one make
Na me, when they talk say na me dey the off, abeg. Abeg,